Alrighty, so this video we're going to continue our discussion about radioactivity and nuclear physics and discuss specifically the three main types of radiation you're going to find when you have radioactive materials. And so we're going to assume we have some element, some atom that's radioactive, and it can decay. And we'd like to know how can it decay and what does it decay into. And the first thing to know is there's three main types. The first is called alpha decay. Now the little symbol for alpha is of course the Greek letter alpha. What is alpha decay? Well, it's when you have a parent nucleus, and P will stand for parent nucleus, and it decays. So this is going to look kind of like a chemical reaction type equation. It decays by alpha decay, and when it does that, let's say the parent nucleus will have, let's say, an atomic number of Z, so that's the number of protons, an atomic mass, we can call that A, that's usually what chemists label them. So here, Z is atomic number, and A is atomic mass. And of course, atomic number is the number of protons in the nucleus. The atomic mass is the number of protons plus neutrons together. So you have a parent, it decays, and it decays into some daughter and an alpha particle. Now, when this decay occurs, you always see the same type of thing happen. First of all, the alpha particle is a particle which has an atomic number of 2 and an atomic mass of 4. Okay. And then, to figure out what the daughter is made of, we're going to use the conservation of charge and the conservation of mass. And this always works. The conservation of charge says, look at the atomic number on the left side of the equation. Whatever that number is, better be equal to the total atomic number of the sum of all the parts on the right. So, and the reason that's the way the charge works is because, of course, with actual elements, you have protons and electrons that can give charge. But when you talk about nuclear particles or nuclear reactions, you never worry about what happens with the electrons per se, at least not the electrons that are orbiting. You're worried about what happens in the nucleus. And so you only have to worry about the protons. So you look at the atomic number on the left. In this case, we have Z, however many Z is. And then you look at the right, and you add up all those Z's, and you better get the same number. Well, right now, we have a Z of 2 on the right, so what must the daughter nucleus have so that the total atomic number on the right side is equal to Z? Well, if we already have 2, then this one better be Z minus 2. Because Z minus 2 plus an extra 2 gives you Z. And the left has Z, the right has Z, we've conserved charge. And that always happens. This is a good thing about nuclear reactions. They are actually very, very easy to solve because of these two rules. They always follow these two rules, and so you can always count on them. The first rule, the total atomic number must be equal on both sides of the reaction. The other is conservation of mass. and that says basically the same thing, only instead of looking at the atomic number, now we look at the atomic mass. So on the left, the atomic mass is A, some number A. What do we have on the right? Well, we already have 4 from the alpha particle, so the daughter, to add up to A, better have A minus 4. Because A minus 4 plus 4 gives us A. And that's the rule. This is the rule for every alpha decay. You start with some nucleus, it decays by alpha decay, and you get an alpha particle plus a new daughter nucleus whose atomic number is 2 less than the original and whose atomic mass is 4 less. Now, we can investigate this a little bit and discover, of course, that what is an alpha particle? An alpha particle is a nucleus with an atomic number 2 and an atomic mass of 4. So all we have to do is look at the periodic table and see what element is atomic number 2. And of course, that's helium. So, alpha particles are helium nuclei, atomic number 2, and atomic mass of 4. So it's 2 protons, 2 neutrons. That's what an alpha particle is. Now, of course, when this was first discovered, they didn't know that's helium. It's just some new particle came out. But now that we know what the particle's made of, 2 protons, 2 neutrons, we know, oh, that's helium. And then the daughter, of course, we would look at its atomic number and discover what element it would be. So let's look at an example. Here's an example of alpha decay. Let's say we have something like thorium. And thorium, if you look at the periodic table, excuse me, it's got an atomic number of 90. And let's say its atomic mass is 228. Okay. And I say this thorium undergoes alpha decay. What will you get? This is the typical question or calculation you'd have to figure out. You start with this nucleus. I tell you the type of decay you're going to have. You tell me what are the results. Well, first thing you know is you're going to have helium 2,4. I mean, that's automatic. You hear alpha decay, you know you get this helium nucleus first. But then you get something else, which is what's left over. So what is left over? Well, whatever the thing is, its atomic number has to be 2 less than thorium's. So instead of 90, it's 88. And we know its atomic mass has to be 4 less, so 224. And so now all we got to do is look at the periodic table, look up what the heck is element number 88, and it turns out it's radium. And there we go. So a nice, simple nuclear decay equation. If we know it's alpha decay, we get an alpha particle, which is helium. And the daughter nucleus is always 2 less in the atomic number and 4 less in the atomic mass. Now that's the first type of radioactive decay. There are 2 more. The next is called beta. Now this is interesting because beta decay, there's actually 2 types of beta decay. Okay, first of all, beta. The little symbol is, of course, the Greek letter beta. And we will discuss beta minus first. All right, beta decay. What do we have? Well, you're going to have some parent with atomic number Z and atomic mass A. We're going to be told this undergoes beta minus decay. And what do we get? We're going to get a daughter. And then there's two extra things we get. First thing we get is if this is beta minus, then we get an electron and an electron antineutrino. Now, we know electrons, neutrinos, in terms of particle physics, are very, very light particles. In fact, physicists have almost always thought, until fairly recently, that they don't have any mass whatsoever, but we know now they do. But what's weird about them is they are very weakly interacting. And what that means is the sun, for instance, when all of its nuclear decays, a lot of them, it's producing millions and billions of neutrinos that are being sent towards the Earth and, of course, everywhere else in space. Well, those neutrinos pass straight through us without us even knowing, and it passed straight through the Earth. And it's a rare, rare event that one of those neutrinos actually interacts with something in the Earth or in one of us. So it's very, very hard to detect them. But we know they're there because we can detect them. It's just very weakly. And there's a lot of interesting physics that comes with neutrinos in terms of what's called flavor mixing. Basically, there are three types of neutrinos: electron, tau, and so forth. And they actually mix with each other. They turn into each other somehow. And physicists are trying to figure out how this happens. It's still a mystery right now. But for now, just know a neutrino is one of the particles that's produced here. And in fact, it's the antimatter version of a neutrino. That's why there's a little bar on top. Now, what do we need to know in order to solve this equation? Because we're going to use the same rules. The conservation of charge and conservation of mass. Well, know that for an electron, the mass we're just going to assume is 0. It's way too light to count for mass. And of course, the same is true for a neutrino. And the atomic number, being a charge of -1, is -1 for the atomic number. And neutrino has 0 charge. Once we know this, now we can use our rules to figure out what the daughter will be. Remember, the left side z must be equal to the sum of all the right side z's. Well, what's on the right? 0 minus 1 is -1. So what must the z of the daughter be to add up to z? Well, it better be z plus 1. And what about the atomic mass? Well, 0 for the neutrino, 0 for the electron, so it just better be the same A as the parent. And that's what beta minus is. Notice what happens. You have a parent, you somehow break something, and you get an electron and an antineutrino to leave. Note, this electron is not one of the electrons outside orbiting the nucleus. This is an electron from inside the nucleus. It came from somewhere. So those go off, but then you have a new nucleus. So it's not the same element it was before because it's a different atomic number that has one more proton, but the same number of protons plus neutrons. So what does that mean? If you have a nucleus and it changed, and the way it changed is now it's got an extra proton, but the number of protons plus neutrons is the same. Well, the only way this could be true is if you took a neutron and you turned it into a proton. Because if protons plus neutrons is the same number, but protons went up by 1, neutrons had to go down by 1 for this to happen. So what really happens is in beta minus, a neutron decays into a proton plus an electron plus an antineutrino. So inside the nucleus, one of the neutrons suddenly breaks into pieces And what it breaks into is a proton and an electron and an antineutrino. The electron and the antineutrino go flying out, but that proton is stuck because of the strong force. And so now the atomic number has gone up by 1. You now have a new element. So let's do an example. The famous example, and in fact, when you get into lab and we do experiments, you're going to see this particular example, is let's say you have strontium. Strontium is atomic number 38. And let's say its atomic mass is 90. You're told that this strontium decays by beta minus decay. And I want to know, what does it decay into? Well, you know you have the electron and antineutrino. But what's the daughter? Well, I know in beta minus, I gain a proton, so it's something that has 39 protons, but its mass doesn't change, so it still has 90. And then I look at the periodic table. What is element 39? It is yttrium, capital Y, yttrium. And that's beta minus. Beta plus, well, obviously it's going to be very similar. And in fact, if you were forced to guess, you could probably guess what happens. You have a proton, Za. I mean, not a proton, I'm sorry. You have a parent. It undergoes beta positive. You get a daughter. This time, instead of an electron, you get what's called a positron, which is the antimatter version of electron. And instead of an anti-neutrino, you get a normal neutrino. So what's a positron? Well, it's an electron, but with positive charge. So it's got +1 for the Z, but it's still got 0 for the A. And so to balance everything, the A is going to remain the same, but the Z now is Z minus 1. And so for this, what happens is a proton decays into a neutron plus a positron and neutrino. So it's like the antimatter version. Instead of an electron, you have a positron. Instead of an antineutrino, you have a regular neutrino. And instead of a neutron turning into a proton, you have a proton turning into a neutron. Okay, that's the difference between beta minus and beta plus. Beta minus occurs much more readily than beta plus. It's hard to make beta plus happen because neutrons are slightly heavier. So if it's slightly heavier, then it can easily break into something lighter, which is a proton. But if you have a proton, which is already lighter than a neutron, how do you make it decay into something that's heavier? Well, you have to feed it a lot of energy. And that's why it doesn't happen as often as beta minus. So that's beta decay. We got one more to go. This one's the easiest, gamma decay. The symbol, of course, Greek letter gamma. Gamma is the easiest because what happens here is you have a parent, Za, undergoes gamma, and you get a daughter plus gamma radiation. Now this, of course, is just energy, or light. So obviously, if the particle decays, but you don't get any things out of it except energy, then the daughter better be exactly the same as the parent. There's no difference. It's the same nucleus. It's just that you gained energy. You got energy from something. So this is the kind of thing like you fed a lot of energy into the nucleus, you hit it with a lot of light, and all the particles were moving around, jiggling very hard, and they were very excited. And of course, just like with electrons, they don't like to be excited very often. Same with the nucleus. So eventually the nucleus wants to calm down, get down to its ground state, it lets off energy. And when it lets off energy, it lets it off as light or energy. And so you don't change the number of protons, you don't change the number of neutrons, so your element's the same, your nucleus is the same. It's just that you lost energy from the nucleus. And that's gamma. And that's it. That's the three main types of radiation. What should you be able to do? You should be able to be given a problem like, let's say, I give you uranium 92, and let's say 234, and I tell you this goes by alpha decay. I want to know, what do you get? Or maybe I say you have plutonium 94, and let's give it 236. And it decays, and let's say I tell you you get an electron, an antineutrino, and neptunium. What kind of decay is this? These are the things you should be able to do. Here's a list of reaction equations. Fill in the blanks. Or you have this element, it undergoes alpha decay. What does it become? What are the reactants? And what are the things you get out of it? Okay, so I will be given an assignment with a list of these types of reaction equations on it for you to have for homework, just to make sure you understand what's going on. But as you can see, the method for solving these is very easy. All you have to do is remember these two rules. The Z on the left must be the Z on the right if you add them all together, and the A on the left must be the A on the right if you add them all together. If you follow those two rules, you're going to be golden. So that's all I have for you for this video. If you have any questions, of course, email me, let me know. But until next time.